Hello, everyone.
How's it going?
All right. So we had our big midterm, and I wanted to make sure you guys are not completely stressed out about that. So once I get more people in here, I'll discuss that for a second. Let me go get some coffee while I'm waiting. Anyone have any questions while we're waiting?
Yeah, I have one question. Um, did you get my email that I had sent out a couple days ago?
I think I remember seeing an email. Let me double check it real quick.
It had like the subject line, uh, PHY 241 extra credit question mark.
Yeah, there you go. Yeah,
Okay.
I thought I remember even applying to that.
Yeah, no, I was like hoping you'd reply, but no. Uh,
Yeah, yeah,
so I
yeah. I
guess
did.
you did reply, or
Yeah, I did. I'm looking at my reply right here. I'll send it again in case you didn't get it. You
yeah,
see, it
because
went to you and me.
let me see if I can find my email.
Yeah, about the
Okay, I
extra
see
credit
it.
stuff, right?
Yeah, okay, I see it. It was just this morning. Okay.
Yeah. I hate that. I hate that it sort of strings it under the previous email. So yeah, that's the big deal. Sometimes I offer, and this is for everybody. Sometimes I offer various problems as the semester's progressing. Where
Mm-hmm.
you've probably seen me make a couple mistakes, and I'll say anybody can find my mistake. I'll get you this, or anybody can uh, tell what I did wrong there and write it up. I'll do this, or if you'll solve this problem, I'll do it. So those are ones. But I also sometimes put chapters, like I'll skip a chapter, but I'll put that chapter in and say, this really would be good if you covered it. So I'll put it in as an extra credit homework. So that'll help you as well. Uh, the only other thing I've ever done other than that was actually allow students to do a book report. If you wish to do a book report, I mean, most people in the sciences like me read kind of slowly, so you might you might not be up to doing a book report in the time we have left for a semester for the semester. But that's something I could offer as well. So if you're interested, I've got a list of books and a very detailed way about which people have to go to do their book report. And if you're interested in doing that, I could do something.
Uh-huh. Do you know like say like I did pretty bad in the I'll ask questions after class.
Okay.
Uh
Yeah. So that's part of what I want to say. Everybody's getting in now. I've got 27 students in here out of I think 45 is how many students I got in the class. So this is a pretty good number. I will tell everybody that. So our test averages are normally for the online test. What happened to you, baby Yoda? Sorry. Uh, my test averages for the online test, which are, you remember, open book, open notes, all that good stuff, but limited time. They normally run from the mid 80s to low 90s. That's a very typical average for those tests. And that's because students are, one, they're really relaxed because they're able to look at their book and all that stuff. And two, they're really able to look up stuff. And some students are really quick. They got that Google foo, if you will. So those grades are high, and I make them a fairly small part of the course grade just because of that. But I want the ultimately you to be able to learn the material well enough that you can do well on the other type of tests. Those test averages are usually from the low to mid 50s to the low 60s. Okay. So if you're within, say, if you made, say, in the low 40s or higher, you're probably sort of the norm. Okay, you're a little bit below the average, which is obviously not good, and the average isn't necessarily good either. But you're not in anywhere where you need to really panic. Let's put it that way. So that's what I want to let you know. Yeah, if you scored in the low 40s, that's not good, but it's really not as bad as you think because we're going to have another opportunity to do better on the final, and hopefully from this experience you've learned how important the practice tests are. And basically your job should be, okay, Mr. Younger's covered the material from the chapter. I want to go through and make sure I can work all the examples in the book. And I want to be able to do that with the book closed so that I actually know what I'm doing, and maybe can even articulate in my mind why I'm doing what I'm doing. And then I'm going to do the homeworks, maybe the conceptual first, and then do the regulars. And then when you're done with that, the rest of your time should be spent on practice tests, because the practice tests are made up of the bank of questions that the test will be made of. I would say, taking a 90 on a homework as opposed to 100 would be infinitely better doing that while taking, say, 10 practice tests instead of 5. So I think that's your best bet, because the practice tests are real. They're quick, so the time's limited, but they're using the real problems. And if you treat them properly, in other words, not looking up the answers and stuff like that, then you'll get the best results. So the big deal with physics is, if you've taken another physics class before, and just like math, you have to solve a buttload of problems. And a lot of them are just little simple problems, but still, you just got to do it. So that's what I'd say is the big takeaway from the midterm. The other thing is I actually watch out for my students. So there's going to be a time towards the end of the semester where I make an offer to you guys that might be able to help this midterm. So just know that's coming as well. So don't fret it too badly. If you want to drop, I completely understand. If you're scoring in the low 40s, your chances of getting an A are a lot less, but your chances of getting a B are still pretty good. Okay. Maybe, like I said, maybe not an A, but definitely a B or a C. And generally speaking, I don't get too many students actually fail. No one gets a C, or even very seldom does anyone get a D. And if they got a D, it's like they just didn't get it. So, and that needs to happen. If you just don't get it, I'm okay with you using this course here, but you need to take it again somewhere else once if you're going to be an engineer or somebody that needs it. Okay. Yeah, C's get degrees is a perfectly reasonable motto. And if you're going to stay transfer within the Virginia community college system, within the Virginia university system, it's my understanding that just like North Carolina, if you have an associate's degree from TCC or some other BCCS school, you're automatically accepted as a junior to the new school. So getting a C versus getting a A isn't going to harm you. Where it will harm you is if you go to graduate school and your GPA is bare minimum below a 3.5. Okay. That's sort of, actually, they normally say the minimum's 3. They're not going to consider an application if your GPA is less than a 3. That's definitely the case with graduate schools, but most graduate schools really don't want to look at you unless you got at least a 3.5. So that's the only thing. And most universities, once you transfer there, they do take into account your grades at the previous institute. So, and they don't necessarily show you that on your GPA every semester of your report card. They don't do that until the actual graduation time. At least that's been my experiences. So, any other questions?
Yes. Do you get my email?
So yeah, C's get degrees. People that go to med school and get nothing but C's, they become doctors too. Uh, I would much rather you have a C that was hard fought by you trying to figure out how to learn than you getting an A and becoming really proficient at looking stuff up. Okay. Or memorizing answers that you've seen before. Those are not learning techniques. And I've seen people who literally built their whole life around this fake degree they got, and it's not a fake degree. It came from a accredited institute, but it they just didn't learn because they cheated their way. And I don't say cheated in the worst sense. It's cheated, but in the sense that they used everything that was available to them, and in some cases they did actually probably cheat by doing stuff online that you wouldn't be able to do back in the old days. And they ended up having a degree about which they didn't really have a knowledge base, and they bought houses and cars and had kids all based on that income, only to find out later their employer fired them for being incompetent. It's happened numerous times. It happened in one case. It happened to a man who was, I think he's probably 56 years old. He couldn't. He was an engineer, and he could not calculate the volume of a cylinder. He basically had made up a spreadsheet for everything he did in his engineering career. Someone hired him thinking he was this really good engineer, and he was sending me off to do calculations that he couldn't do. And I didn't realize that. I was just excited about the chance to do calculations in the engineering firm, and people were really, oh, Billy's good, he's great, blah blah blah. Well, then the boss told me, okay, I need you to stop doing that for him. I was like, okay. And then he found out later that he was actually using spreadsheets for everything, and then whatever he couldn't do himself, he just gave to me. Meanwhile, I was making like $25 an hour, and he was making like 72. So,
Wait, Mr. Younger, Professor
yes.
Younger, are you serious? Like, did he not know how to calculate like just like a cylinder, or was it more specific?
No, it really was a cylinder. It was literally how much concrete do you need for a cylindrical pier. He had a spreadsheet that did rectangular piers, concrete piers, and he designed a concrete pier. Well, the customer wanted a cylindrical pier, and he said, well, I don't have a spreadsheet to do that. And he said, well, you just do it yourself. And the guy was like, well, and I knew he could have looked it up. I mean, what idiot don't know pi r squared h? But still, he was at a point where he didn't feel confident enough in himself because he'd been leaning on these spreadsheets so long. So they literally fired him. It was a really big deal. It was kind of funny to watch.
Yeah. Unless you have like really good skills in another area to compensate for that loss in like calculative abilities,
Yeah.
like you're in a big trouble.
Well, yeah. Well, when you get in your late, 50s in the engineering field, you're more about being a businessman. So he was really good at schmoozing people, and he had these various what we call planned urban developments, PUDs is what we use for it, and that's basically where you have a probably 10-20 year contract with a company that's developing butt ugly, dirty, flat land and woods and stuff.
Okay.
A lot of that has a lot of technical details that go into it, and he had spreadsheets for all that, but his deal was going and getting those types of jobs. So that's why he was hired in the first place at such a high salary.
How much was he making a year?
This was 99 or 2002, and he was making 95,000 a year.
That's really good.
Yeah, on the Outer Banks, which doesn't have jobs like that on the Outer Banks.
Wow, that's awesome. I go windsurfing there.
Yeah. And like I said, it's not. So it was more man, and he went to Purdue, so he probably had a good education, but he just lost track of that. So that's a big thing. And then other cases, I've seen one guy had only an associate's degree, and he was doing their structural engineering calculations, and he was really bright. He knew what he was doing, and he taught it all to himself. Okay. But they were paying him crap because he wasn't a licensed engineer, and he had to get someone else to stamp it.
Oh, so wow.
That's the other side. Knowledge can help you, and that's what I was doing. I was just wanted the knowledge of it.
Yeah, if you get both best parts of both worlds, you can really excel.
Yep. All right, so I guess we'll get into the stuff. We've got a few more things I want to finish in Chapter 8 before I jump into Chapter 9, which is momentum. According to our schedule, I think we're doing pretty good. So let me open up by asking, does anybody remember what we were doing before the break?
Professor Younger?
Yes.
Do you get my email, my exam work?
Oh, yes, I did. Well, no, the first one I got from you didn't have any attachment.
I resent it.
Okay, yeah, I did see your name just a few minutes ago come across my transom, if you will. Oh, and I wanted to mention also, guys, I might have a lot of people in here that didn't take the midterm. I think there was 7 or 8 people that didn't take it. Most of them for basically not listening to me and not getting the practice midterm respondus done beforehand, because I gave it to you before the spring break specifically so y'all can make sure you get your respondus crap worked out. And I had several students on the order, like 5 or 6 of those 7, had problems with respondus. I have now opened that back up. Anybody that has now got their respondus issues worked out can take that at any time today, as I sent in the email. It opened up at 12:01 a.m. this morning and will close at 11:59 p.m. I don't know if you started at 11:50 p.m. if it's going to stop you working at 11:59. I don't know exactly how that works. So I would say start at least 75 minutes before 11:59 p.m. because this is the last chance I'm giving you. And even then, because you missed, it wasn't unfair it was unfair to everybody else. You're getting 7 points deducted. If you haven't got the respondus worked out, I've also made arrangements for everybody that missed to take it at the testing center today or tomorrow. So you've got today and tomorrow to take it. If you miss these opportunities, you're going to be probably dropped from the class. Contact me if something happens that makes you miss it, and I might be able to work a deal with you. Or if you let me know beforehand that was something going on, like I had one student had to leave and wouldn't be back till like next week. That student's obviously not counting in this scenario because they made it.
Wait, so Professor Younger, does that respondus practice exam? I already took the actual midterm. Is that practice one count toward your grade?
No, not the average of all your practice tests counts towards your grade. I made it like an extra 5% or something, above 100% though. So if you get all zeros or never take it, it's not going to hurt you.
Okay,
But
good.
if you get all hundreds, you're going to get 5 extra points.
Okay, thank you, Professor Younger, for letting me
And
know.
that also addresses your question, Miguel. I think it was Miguel that asked. So
Yeah.
anyways. All right, so let's get started. I'm going to share my screen on some problems I worked out. Actually, I had a couple more, but I didn't get a chance to write them up because I'm a busy bee. Somebody just asked me a question, but I lost the chat. Let me see if I can see that. There it is. Jasmine, no, I don't recall doing that with your test, but some people did. Okay, so all right. So this is the problem we're working here. I'm going to shrink this little screen out to the left a little bit so it's out of my way. So problem 1 is a child's toy consists of a vertical tube with a vertical spring and latch system inside of it. When the accompanying 20.0 gram ball is pushed down fully a distance of 4.00 centimeters, it makes a clicking noise as it latches in place. I think y'all can picture the toy we're talking about now. Then when a button is pushed, it releases the spring and the ball shoots up vertically upward. If the spring constant of the toy's spring is 100 newtons per meter, A, find the maximum speed the ball will achieve, and B, the max height the ball will achieve. Okay, so that's our first problem. It's a conservation of energy problem. I'm assuming that air resistance is negligible. I'm assuming that the friction between the ball and the little tube that you're sinking it into is negligible. And we're going to do some calculations. Okay, so let's go ahead and stop sharing the screen for a second and show you my drawing of the actual object that I think I'm working on, which is not me, but the paper. So let me turn it on the right camera. So what I'm picturing here is like a toy gun that's spring loaded. You're going to have basically a spring like this. And I'm going to draw it right now as if it's compressed and latched. So here's the little latch mechanism, say. And the ball is sitting on it. And the reason I drew it in this space, in this particular position, is so that I can go ahead and show you that I'm going to call the potential energy U equal to 0 there. Okay, and when I say potential energy, this case, I'm talking gravitational potential energy. Remember, we can treat the spring as if it has potential energy as well, or you can compute it as work done or something like that. I'm going to treat that as just 1/2 kx squared, not even try to name it. Okay, so what we know is going to happen is when I push this little button, that's going to cause this latch to swing loose and the ball is going to shoot upward. So I want to know V max and I want to know H max. Okay, that's really what I'm trying to find out. I know the K for the spring is 100 newtons per meter. I know the spring has been pushed down X, I think I'm going to call that X0 is equal to 4.00 centimeters. And I know the mass of the ball is 0.020 kilograms. In other words, I went ahead and converted it to the proper units. Okay, I have not converted this to the proper units yet. So conservation of energy says the sum of the potential energies plus kinetic energy initially plus work put in is equal to the sum of the final kinetic energy, potential energy plus work out plus E loss, all that good stuff that I showed you before. In this case, I'm just basically going to say 1/2 K X0 squared is the total energy we have initially. Okay. Because it's got a U for gravitational potential energy equal to 0 here. The only energy I put in is compressing the spring. That's 1/2 K0 squared. That's the total energy. So I can say this is with a capital T subscript if I want it. I think somebody just came out. There it is. So that is the initial total energy. But what's going to happen is that potential or that total energy is going to go into potential energy, which is mg times h, plus kinetic energy, which is 1/2 mv squared, plus there's some range over which it's going to have a height plus 1/2 k x squared. In other words, if I go to 2 centimeters, I haven't dumped all the energy, so I have to account for the 2 centimeters that are left in here. So that's really what my equation for total energy is. This is my conservation of energy equation. And I just showed you that as total energy because that's all that we could get out of it. So with that in mind, I can take that equation and I want to find where the maximum of kinetic energy is. My instincts tell me the maximum speed and therefore the maximum kinetic energy should occur when the spring has fully extended itself back to its equilibrium position, because at that point it's going to start going up slower than the ball and the ball will leave there. So instinctively, I think the maximum velocity will occur when the compression of the spring is 0. In other words, when the potential energy is mg times 0.04 meters, right? But there might actually be a slightly bigger speed a little bit before it. So I'm going to show you a couple of ways we could do that. The first thing I'm going to do is take this energy 1/2 k x 0 squared equals mgh plus 1/2 mv squared plus 1/2 k x squared. And I'm going to solve it for v. And I'm going to do that by first multiplying everything by 2. Okay. And I'll get kx 0 squared. Because I want to get everything over here, I'm going to go ahead and start subtracting terms. So I'm going to say minus mg, or minus 2 mgh, sorry about that, minus kx squared is equal to mb squared. Everybody see what I did there now?
Can you just bring it in a little closer?
Yes. That's a 2, not a z. Okay. So now I'm going to keep on trying to solve for this v. I'm going to divide both sides by v, and I'll get v squared is, or excuse me, by m, and I'll get v squared is equal to k over m x 0 squared minus 2gh minus k over m x squared. And that should be it. Now I can say v is equal to the square root of that junk. And this time I'm going to say k over m times x 0 squared minus x squared minus 2gh. Okay. Now, I think you'd all realize that the instant it leaves the spring, so the spring's going to completely extend to its equilibrium position, which is right about here. At that time, the spring immediately starts getting pulled backwards by the spring's tension and by gravity, right? So it's definitely going to go slower than the ball at that point, because the ball has its momentum going upward and only has only has gravity pulling it down. So this extra little kx that's pulling it down, pulling the spring lid down, is clearly going to make it go slower than the ball. So the absolute highest position x that could result in the the ball having the highest speed is when h is equal to x. Does that make sense to everybody? Or meaning h is equal to this particular x. Let's put it that way. Does that make sense to everyone? the reason why I do that is because now I can reduce this to say one particular variable, namely the x, and I might be able to find the maximum velocity by taking the derivative and setting it equal to 0. So I'm going to give that a try. I haven't worked this one out. I just came up with this method a second ago. I had another way of showing you, but I just came up with this. So let's try it out. This answer is absolutely correct. I'm going to make the initial argument that at least for the first 4 centimeters, which is where I expect the maximum velocity to occur, I expect that's going to occur while h is actually equal to x, because x and h both start at u equals 0, right? So let's make that. So I'll say v of x is now equal to the square root k over m x0 squared minus x squared minus 2gx square root. Now dv over dx is going to become, well, it's the derivative of u with respect to, or excuse me, the derivative of v with respect to u. If I pretend u is everything under the square root, then it'll just be 1/2, because that's the power of the u, times u, which would be, and that'll be u to the negative 1/2, which would be k over m times x0 squared minus x squared minus 2gh to the negative 1/2 power. Now I've got to take times the derivative of u with respect to x, and the derivative of u with respect to x, obviously this term is going to be a constant, the k over m x0 squared, but the negative k over m x squared is going to become negative 2k over m x, and then the negative 2gh, or excuse me, negative 2gx, which is what this was supposed to be. Let me use my error corrector. Everybody see what I just changed? I forgot to change it to an X, even though I made a big hullabaloo about doing it. And this will say minus 2g, all of that in there. So dv dx equal to 0 becomes this 2 will cancel out with those two 2's. In other words, I can factor out a 2 from that polynomial, and that'll factor out with this 1/2, so I don't need it. I'm going to say now I've got k over m times x, negative k over m times x is minus 2g. That makes sense. Over the square root of k over m x0 squared minus x squared minus 2gx. All that has to equal 0. Okay. Well, clearly the denominator is not going to play a role in this equaling 0. So I think what I'm going to get is negative k over m times x minus 2g is equal to 0. So that would say x is equal to 2g over negative km over m. That would be negative 2gm over k. So let's see what happens when that's the case. When x is equal to negative 2gm over k, do the units even work out right? Because that's one thing I want to check, just to make sure I didn't make a careless error. Let me pull this up to the screen so everybody can see it, and maybe someone will find any errors I may have made. So notice that is the derivative of the thing inside the parentheses that has a negative 1/2 exponent on it. I am saying km x0 squared minus km x squared. When I take the derivative of negative km x squared, I get negative 2k over mx. And when I take the derivative of negative 2gx, I get negative 2g. So that's where that last parenthetical comes from. Then I put it all back together, set it equal to 0, because I'm trying to find the maxima or the minima. And this negative is what's bothering me. But yeah, this negative is what's bothering me. So let's check these units to see if that even works right. So G is meters per second, and that is M. So that's actually a unit of newtons. And this is a unit of newtons per meter. So the newtons will cancel out and I actually get a meters distance. So let's see what that negative 2G M over K actually is. So X max is supposed to be, and I'll put a question mark over it just because I'm not sure if I made any kind of errors, but I'm leaning towards it being 4 centimeters. But let's see what this comes up with. I'm going to say negative 2 times 9.8, and the negative I've got to deal with in a second. Now, it actually might mean something different and give us a minimum speed of it as if it was falling. And the mass is 0.020 kilograms. And all of this will be divided by 100 newtons per meter. When I do this calculation, God only knows what's going to come out. So I'll say 2 times 9.8 times 0.02 divided by 100 equals, ooh, very close actually. That's kind of weird. 0.0039, actually it should be negative 392 meters. And that is the negative third. 1, 2, 3. Yeah, that's right. So that is actually suggesting down below here, if I actually did a plot of what this velocity looks like, let's do that real quick. So I'm going to stop sharing screen a second. Actually, no, I'm going to do something real quick. Hold on. I'm going to open up Desmos, and this was actually the original plan of what I was going to do to show you how to figure it. I'm opening up another window in, I don't know if I'm doing it with, oh, I'm doing it in Chrome. And I'm going to do graphing calculator. Okay, so I've got that open. Now I'm going to do a share screen with that window. Okay, so let's check this out. I've got V is equal to a square root. So I'm going to say Y equals, let's see what's down here. Square root of, and now I'm going to actually put the numbers in. The numbers are K, which is 100, divided by 0.02, that's K over M, times X0 is 0.04 squared minus X squared. Put a parenthesis there. And then I'm going to say minus 2GX. And let's see what this graph looks like. Now I can close this back down. I'm going to make this window a little bit bigger. And now I'm going to zoom in. So it does look like the Y, which is the velocity, does ultimately have a maximum. And it looks to me, see, there you go. That is the problem. The Y does have a maximum, but it's at a negative X value, which is negative 0.002 something. And I got 0.004 roughly. So evidently this is not a maximum. In other words, from X equals 0 on up, the velocity keeps decreasing, decreasing, decreasing. So I can't get anything else out of that. Anybody see any errors with anything I made? So this is a good try, but it gave us sort of what I think is an unphysical solution. Okay, it gave us a negative, and that often happens like when you're solving for time, when you use the x equals 1/2 at squared plus v0t plus x0 equation. Sometimes you will solve that, and you're like, especially if you're doing a projectile that's fired like off of a cliff. Why are you looking at the paper? You should be looking at me. Hold on. So sometimes when you use x equal 1/2 at squared plus v0t plus x0, and you're say firing something off of a cliff like that, and you say at what time does x equal, or excuse me, at what time does the height equal 0? What you'll get is this time t over here where it actually hit the ground, which is true 0, and the y0 would be the height of the cliff, but you'll get a negative number. And what that represented was the parabola that started back behind the cliff. So the cliff was like here, say, or let's say the cliff was here. If you imagine a parabola that came up and just happened to go right through the barrel of whatever you shot that thing out with, and it landed over here, that negative time represents where it would have been fired from the ground height. So that sometimes happens with physics equations. It works out because that particular equation applies to a parabola that was created by something shot from the ground with a bigger speed than something also it applies to with a parabola that was created by something shot from the top of a cliff with a slightly smaller speed and a slightly smaller angle of incline. So that can be what that happened. And I'm thinking right now that that negative is what's going on here. That might be something that's not that physical. So the other option was, and this is what I ultimately did, is I calculated it when the compression of the spring was exactly 4 centimeters, and I calculated that velocity. So let me show you how I do that, and then I'll show you how I can try to see if that makes some sense as to when the maximum velocity is. That curve that we got from Desmos makes me think I might have made an entirely bad mistake, because that velocity goes down constantly with x, and it actually should go up, 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 and then start to go down, down, down as it's released from the spring. But it's only valid, of course, up to 4 centimeters. But that graph didn't even include 4 centimeters. It only went up to, let me see. Yeah, it only went up to like less than 0.1. Oh, wait a second. 0.1 is actually 10 centimeters. Oh, so it only went up to 0.381 was, okay. So it actually went to 3.81 centimeters was where that value actually stopped, because that actually gave us a negative under the square root. So it must be that it has a minimum somewhere in there, but not a maximum. So I'm just looking back at the curve real quick. So now I'm going to go ahead and go back to my document cam and say, this evidently didn't pan out to give us a maximum. Maybe it only has a minimum, but that definitely showed a maximum on that Desmos graph. So what I'm going to do now is I'm going to go with my physical assumption. And my physical assumption was that as the spring goes up, it's applying a force k times x from Hooke's law that's speeding it up, speeding it up, speeding it up, and ostensibly would be greater than the force of gravity, because the force of gravity is only going to be about, what, multiply this by 10, and that's an overestimate. The force would only be 0.2, whereas the force here would be 4, because 100 times 0.04 is 4. So we're going to get 4 newtons up and only 0.2 Newton, less than 0.2 newtons downward. So this is going to speed it up, speed it up, speed it up. And of course, the amount it's speeding it up is slowing down as it gets higher and higher. And then when it gets to the x equals 4 centimeter mark, that's going to, of course, give us a what I think would be a maximum velocity, because then once it leaves, it's going to start to slow down under the force of gravity. So let's do that. Let's see v at 4.00 centimeters. That's going to be equal to the square root of 100.
Can you move that up?
Yes, thank you. I'm glad you told me that. I wasn't even paying attention. So 100 newtons per meter over 0.020 kilograms times 0.0400 meters squared minus obviously 0.0400 meters squared minus 2 times 9.8 meters per second squared. That's actually 3 sig figs. I just left it off. Times 0.0400 meters. Square root of all that. This turns out to be basically square root of 5,000. A Newton is a kilogram meter per second squared. So I just divided the kilogram out of that. Now it's a meter per second squared divided by meters and then times meters. So this is just a meter squared per second squared times, of course, 0. Minus 2.8. That's the problem. Let's check my original stuff. When I brought that over here, that should have been, yeah, it would be negative. So I guess that works. Huh. I'm getting a negative under square root. That's not good. I did not see that last time because this didn't cancel out last time. Wonder why that's so. Well, this just went to crap in a handbasket really quickly. I worked it all out before. Oh, that's why I left off a whole term. Well, that's crap. So the problem is I tried to make sure I did it correctly and took into account this extra 4 centimeters that it drops. A lot of times you sort of assume the zero potential energy would be right here. And then when you do that, this would be a negative height. That might have been a better way, and that might have gotten rid of all this negativeness. Because right now, y'all see what happened when I get to x equals 4 centimeters. I see that this whole first term is negative, but I end up therefore getting a negative under the square root. And that does not bode well. So I want to check, make sure all my equations were originally right. My total energy was 1/2 k x0 squared. Plus later on, that's going to be converted to mgh, where h is the distance from here up. And plus 1/2 mv squared, where v is the velocity it has at any point there, plus 1/2 kx squared, where x is the distance from here up, but can only exceed, it only goes up to x equals 4, and then it of course disappears. So at x equals 4, that should come to a stop. And I guess by me changing the x into the h, or the h into the x, that's what produced a non-physical problem. It's sort of, it's like I'm saying this is a piecewise function. In other words, it's this right now for x less than or equal to 0.0400 meters, but it's mgh plus 1/2 mv squared for x greater than 0.0400 meters. I know that's exactly the true energy equation. I guess by not treating it that way and just pretending I can later ignore that when I do the later part of the problem, I think that's what introduced me to a negative under the square root. Because using this function like this, I really can't. And by trying to compute what that was, that led to a problem. So what I'll do is rewrite this. Let's call it instead, let's treat it all as if it's always going to be x greater than 0.04. Or actually, let's do this. Let's call this the x equals 0. or in the u equals 0. If I change that, I'll write this all in green so you can see the new solution. So if I call that u equals 0 and say that's no longer the case, then I'd have 1/2 k times negative x0 squared. Again, that's not going to matter because the negative is going to be squared. And another student came in, I guess he got knocked out. So negative x0 squared, that's the total energy. So I'm going to set that equal to 1/2 mv squared. That's the kinetic energy it's going to have as a function of x. Plus it's going to have mgx. So I no longer have to call that h. And then I would say plus, this is the hard part. No, I'm actually going to leave the 1/2 kx squared because I'm going to only deal with, no, I'll deal with x equals plus 1/2 kx squared. And this will only go for x less than 0. And it might even be x is equal to 0. Yeah, it might even be x equals 0, but I'll say that. So now if I go and try to solve the equation for x0, I'll get k x0 squared equals, I've already multiplied by 2, in other words, mv squared plus 2mgx plus k x squared. Again, I'm going to get the same sort of type expression. I'll say v is equal to k over m times x0 squared minus x squared. And then that'll be that from coming over there. And this will be minus 2gx. So that's the exact same expression, but I know the rule that x has to be less than or equal to 0. Yeah, it's got to be, if it's actually 0, that's going to be 0. And that's going to be 0. And then I'll just get this. Okay. Now, if I try to plot that, let's see what happens. Actually, it's the same thing, so I shouldn't bother, except for, yeah, it's literally the same thing. So it's not going to have a maximum because we know the graph, but now I can calculate the v at x equal 4 centimeters. So let's see what the v is going to come out to be. So v at x equals 0. So in this case, this is going to be 0, this is going to be 0. It's going to be v is equal to the square root of k over m times x0 squared. And lo and behold, I get square root k over m times x0. And that is actually right. So whatever I did here worked out fine. So I'm going to say v at x equals 0 is now going to be, and I don't have any pesky negatives under square root, it's going to be the square root of 100 newtons per meter divided by 0.020 kilograms. This actually turns out to be 5,000. So it's the square root of 5,000 times 0.0400 meters. The units all work out like they're supposed to. So I'll say times 0.04. And I get the velocity is, yeah, this is what I calculated earlier, so that makes me feel better, 2.83 meters per second. And it's actually, just to carry extra digits, 2.828 meters per second. Okay. So that is the actual velocity at that. If I want to test and see, because I don't necessarily trust my ability to find that maxima from the equation, what I did earlier, and this was the other thing I wanted to teach you, is I wanted to say, okay, what I would do when I run into this, and I'm not really sure if maybe there's some instant just before x equals 0 that the velocity is faster, then I could try let x equal, instead of 0, let x equal negative 0.0001, are negative 0.001, and try all these successive values. And basically, when I did it earlier, I ended up getting a slightly lower velocity, so I could see a trend that it was actually increasing constantly. This equation might actually work a little better because you could actually treat x equals 0 as something, but still, I don't want to mess too much with that. I've now got a velocity. That's the velocity when it leaves it. If you want to try, for x equals negative 0.00, because of the depth was 0.04, I would try at least 0.0039 and 0.00399 and 0.0039999. And what you'll see is you should get slightly smaller and smaller values. And from the looks of this, when this is x.399999 or whatever, then this is going to be slightly bigger than that. So I'll get basically.
It's a little off screen if
Yeah,
you're
sorry
trying
about
to
that.
gesture something.
Yeah, if I actually plug in 0.039999, this is going to get closer and closer to 0, and then this is going to be, of course, negative something, so that'll be positive. So I start getting this thing being the major term, and I think you can see from that ultimately gives you a smaller magnitude than this one. So it does turn out we were right with our physical assumption that when it got to its equilibrium position, the maximum ball velocity would be there. So now I got to answer the other part of the question, which is way easier. And what's the max height? So the max height for part B, sorry about that long diversion there. We take 1/2 k x 0 squared is equal to, now in this case, the spring is completely unloaded. That's why I have to go back to this part. Remember, this is for x greater than 0.04. I have no more energy in the spring. We're assuming the spring's massless, so that doesn't matter anymore. So I just got this term over there. That's why the potential energy had a piecewise feel. So this is going to be equal to 1/2 mv final squared plus mg h final. Well, if it really is h final, if it had any more velocity upward, it would go higher. Or if it was below h final, in other words, it would still have a positive velocity. But if it would, or it would have possibly a negative velocity. But in either case, if I got to the absolute max height, the actual velocity would be 0. So I'm going to say this is 0, and I get h final is actually given by, now I'll take 1/2 k x 0 squared and divide it by mg, and lo and behold, I get h final is equal to k over 2mg x 0 squared. So h final, the max height, should be 100 newtons per meter over 2 times 0.020 kilograms times 9.80 meters per second, all that times 0.0400 meters squared. Putting all this junk in a calculator, I get 100 times 0.04 squared divided by parenthesis 2 times 0.02 times 9.8. And I put that in parentheses because my calculator knows order of operations properly. If you didn't put it in calculator, in parentheses, it would divide by the 2 and then multiply by the 0.02 and the 9.8. So that's why I did that. And I get 0.4082 meters. So I carried an extra digit, which y'all can't see. I carried an extra digit just for, in case I had to use that for a subsequent calculation. So I would answer part A. The answer is 2V max is equal to 2.83 meters per second. And part B, the answer is H max or H final is equal to 0.40 8 meters. So it made it about 40 centimeters, 41 centimeters up. Any questions on that? Sorry about the bog down, but I thought I found the mistake when I worked it this way. When I worked it this way to prep for class, and didn't, of course, I didn't have time to check that my correction was correct, but my correction was wrong, or at least it hinged on the fact of where we're going to turn X into a negative. So ultimately, I think you saw some good stuff, even though some of it was kind of crappy. Of course, it was worthwhile for you to see how to do that derivative, even though the derivative didn't give us anything remotely meaningful. It gave us exactly what Desmos said, by the way, though. As you can see, if you actually wanted to calculate this mess, it would have came to 0.00392. And I think we got, oh no, that's right, we got negative 0.002, so it didn't even give you that. So I don't know what that is compared to what Desmos had. I don't know if I made a mistake in putting it in Desmos, or if I made a mistake and deriving it before I put it into Desmos, or what. But ultimately, what we had to do is I changed the 0 to be at the equilibrium spot of the spring, and then of course X would be the height, which would be negative initially, negative 4 centimeters, and so on and so forth, and that got rid of all my negative problems. So maybe in the sense of running into a problem, I might have given you a little help there, just because if you start getting negatives under a square root, you know that's an unphysical solution. If you start getting X's that are negative in some cases, or time that are negative in some cases, that's actually an indicator of something that's unphysical. So you have to figure out how to correct it. So sometimes it just happens to be what coordinate systems you use. Sometimes it happens to be that you did bad math. Okay. So anyways, I'll say that's the positive that came out of my screw up, but the rest was pretty much negative. Now let's look at another one that's kind of useful. So I'm going to go back to my problem set. This one says, consider a pendulum made of a massless string of length L, on the end of which is a particle of mass M. So I did all that stuff. I said a massless string of length L and a particle of mass M. By calling it a particle, that just means I'm saying the distance from where the pendulum swings, wing, 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 like this, to the center of the ball, i.e. the center of mass, is L. So that's all. That's the only reason why I put a particle there. I'll say the pendulum's raised so that the taut string makes an angle alpha with the vertical. So that's like theta 0, if you will. That's the initial angle. And what I want you to do is determine the total energy and write an equation for the speed as a function of theta, the angle the string makes with the vertical. So this is kind of a neat little exercise in algebra, or excuse me, in algebra and trigonometry. So that's one of the reasons I wanted you to do it, because it is something that we expect everybody to be able to do in physics. So initially we might have a length L and having a string here. So what we're meaning is this length from here to the center of the ball is L. Oh, let me go ahead and stop sharing screen and show you my camera again. So I'm saying the length from the ceiling down to the center of the ball is L. This is a mass M. What I'm going to do now is I'm going to tilt this at a large angle so it's obvious that it's at an angle, and that angle is going to be the alpha that I was talking about. Okay, so this length again is L, and that goes all the way out from here to here. Okay. The reason why I do that is because I need to figure out what the height is, because the total energy is set up by the initial potential energy. So in other words, when I take this pendulum bob and I pull it out here, I've given it all the energy it has. So the initial energy is mgh. Given by that little h right there. So I got to figure out what that little h is. Well, I know, for instance, if I look at this side, I take the sine of alpha, it equals opposite over hypotenuse. So this would be, say, L sub x, L sub x. That would be L sub x over hypotenuse, which is just plain L sub x is equal to L sine alpha. That's not the one I wanted, so now I'll try cosine. Again, I'm trying to remind you to not jump into thinking you can immediately choose whether I want the sine or cosine. Take a little time and make sure you get it right, because I don't want people thinking in terms of Cosine gives me X, sine gives me Y. That's not always the case. So when I take the cosine in this case, I'm going to get this quantity, which is L sub Y, over the hypotenuse, which is L. That's the one I want. Because it turns out this is L, then H is L minus Ly. Does that make sense?
What does sine x equal?
That
It's-
sine of alpha is equal to L sub X over L. This is the alpha, that Greek symbol there. Let me pull it up closer to it. And leave it unfocused so that I'll make it really clear. So sine alpha equals L sub X over L, the length of the pendulum, just like cosine alpha equals L sub Y over L. Now I'll pull it back down here and focus it again and push it up there. Okay, so does everybody see that H is in fact L minus Ly?
Yeah, I see it.
Okay, so now what I'm going to do is say this is L minus L cosine alpha, which of course is just L times 1 minus cosine alpha. So this is a trick I wanted you to see because everybody, this comes up over and over in various types of problems. So I always want you to be able to work out some of the trig. So the energy total is equal to the potential energy initial, which is equal to the mass times G times L times 1 minus cosine alpha, right? So I'd asked you to calculate the total energy. This is one answer. And now I want you to calculate the velocity as a function of the angle theta, where theta is at some other time, the pendulum is doing this thing, and theta is this angle. Okay. So the total energy is equal to U initial, which also equals U final plus K final. So I will write MGL times 1 minus cosine alpha has got to equal potential energy, which would be MGL times 1 minus cosine theta now, because that's for any particular angle, plus 1/2 mv squared. So that's V, where we could actually possibly get it as a function of theta. What I'm going to do now is multiply both sides by 2 over m. And that will get me GL 1 minus cosine alpha is equal to 2GL. Actually, this should be 2GL. Sorry about that. 2GL times 1 minus cosine theta, and then plus V squared, like that. So now I can solve for V. V is going to equal the square root of 2GL times, check this out, 1 minus cosine alpha minus 1 minus cosine theta. And that should be it. But notice, because I wrote it that way, now I can start doing some substitution. 1 minus 1 is going to make those ones cancel out. And then I'm going to have minus minus with cosine. So it's cosine theta minus cosine alpha, or V is equal to the square root of 2GL times cosine theta minus cosine alpha. That's a horrible looking alpha. So my final answer for this one is V is equal to square root of 2GL times cosine theta minus cosine. I've completely forgotten how to draw my alpha. There you go. That's close enough.
We can't see it. It's
There you go. Same expression I wrote before. I just tried to make a better alpha. All right, so that means you can put in any particular angle theta. So if it was like 30 degrees or whatever, and alpha was originally 45, of course, you've got to have, as you can tell here, because cosine, the possibilities for theta are only up to 0 up to 90. So that's the only range. And if you look at the cosine graph looks like this, where this is 90 degrees right there, right? So cosine is actually a decreasing positive function. So for all angles less than theta, if this angle is smaller than this angle, then I'm going to get a negative number. Or excuse me, I'm going to get a positive number. But if it's actually bigger, then I'm going to get a negative under the square root, and that's impossible. So in other words, we're learning that theta could never be bigger than alpha, or else I'd get a negative under the square root. So that sort of fits what our idea of reality is. If you lift something up to angle alpha, you never expect it to exceed that angle alpha, because that would require a violation of the conservation of energy. Any questions on that?
No, sir.
Okay. So there turns out to be one more sort of thing. I've already talked a little bit about power. So I want to mention that before I go on next time to chapter 29. But power, remember, it's measured in watts. So I'll write it like this and say it's equal to 1 joule per second, which is defined to be 1 watt. Okay. That's the units of power. Joules per second sometimes is kind of handy, so you can see, how much energy is going on. 1 joule per second is about the energy required. The joule part is about the energy required to lift a red delicious apple, a good sized one, from the ground to the top of a kitchen table. So when you're talking about 1 watt, you're imagining a person doing lifting 1 apple from ground to the top of a kitchen table every second. When you talk about a 100-watt light bulb, you're picturing 100 red delicious apples being lifted from the ground to a tabletop in 1 second. So you can see 100 watts is really a significant amount of power. How much would you pay a human to lift 100 apples every second? It would probably be way more than what you're paying for a watt of electricity. When in actuality, you're buying joules, by the way, not watts. So anyways, that's what power is. And we often think of power as the instantaneous rate of change of the work. So I want to put a different W here, so you'll know that that's work, not the watt. Okay. So that's what power is. It's power is equal to the derivative of work with respect to time. If you think of work as F dot dx, then you can get power is equal to d by dt of F dot dx. And of course, that was supposed to be like that. Well, this becomes, if the F is a constant, that's going to become F dotted with, and I'll put a CO in there for constant, dotted with dx dt. And of course, dx dt is what? Anyone know?
The velocity.
Exactly. So if you have a constant force, you just dot it with the velocity and you will get the power. So that's a useful thing. However, you very seldom have a constant force, but that tells you that you can say average power would equal F average, and we put a bar over it to mean average, dotted with V. So that equation still works even if we don't have a constant force. You just have to be careful and know that you're calculating the average power and the average force. Okay, so that's another little thing you can use. The efficiency is something we use as well. And efficiency is, I always define it this way: what you get, and I mean the useful part, divided by what you pay for. Okay, so what that means is basically you can say it's the E out over the E in, but I'll put little quotation marks around it because I want you to realize it's not just the total amount of energy that comes out, it's the useful energy that comes out. But because power is equal to energy per time, it's also P out, again with quotation marks, over P in. What I mean by useful work or useful power, well, for instance, when you make a heat engine can be basically like a piston. So you take a piston and you push up on it, and the piston compresses a gas. Well, that also heats up the gas. And then, of course, if you're talking about an engine like a diesel engine, it heats it up so much because of the huge compression factor that it explodes spontaneously. And then that explosion pushes the piston back down and we get a certain amount of energy from it. But a lot of that energy goes up to heating the actual piston and the piston walls. And only the rest of it goes into moving that piston. So all that heat that went into heating up the walls of the piston chamber and the piston itself is not part of that P out. The P out is only the part that went into moving the piston. So that's what I mean by that. Because if you did it the other way, then the efficiency would always be 100% because it'd be total out divided by total in. But instead we use efficiency to mean what you get that's useful. So E, the efficiency, is E out with, again, quotation marks over E in. Or you can use it as P out in quotation marks over P in. Doesn't matter. And they'll usually just state it as a decimal 0.10, or they'll multiply it by 100 and put a percent symbol on it. All of those are acceptable. It's just something you need to know. So like if they tell you your body can produce a certain number of calories or can burn a certain number of calories per hour, that's really something that can be readily converted to joules per second. So that's the power that your body can take in. But if your body's only 20% efficient and that happens to be 1,000 calories per second, then that means you're only going to get 200 calories out per second. And that's an advantage for us because, like I told you, if you realize that the calorie we deal with in food, like for diet purposes, I just assume you're talking about worrying about being fat like me or something. So when I want to, say, eat a piece of cheesecake, and I look up that the piece of cheesecake has 940 calories, let's say it has 1,000 calories, then I happen to know that that's not just a calorie like we learned in chemistry. That is a capital C calorie, which is the same thing as a kilocalorie, which is 1,000, or actually 1,000 calories, which is 4,814 joules. So 4,418 joules is the amount of energy required to lift 4,814 red delicious apples above the ground onto the top of a kitchen table. That's a lot of energy, right? So that's what my calorie is. Now I'm talking about eating 1,000 of those. That's lifting a million red delicious apples. So when I go to burn those calories off, I have to burn basically 4,814,000 calories to make up for that cheesecake. Well, as luck would have it, when I go to do that, I'm doing so really inefficiently. So if I actually work to get to, say, 1,000 kilocalories, and I've actually done that, then in fact I've gone too far because my body has only been 20% efficient. So I sort of like went in some sense 80% over. So you have this little correction factor because the calories are so horrible that really hurts you. But the good news is you burn way more calories than it says you put out by the inefficiency of your body, which, by the way, your body is actually quite efficient compared to a car engine, for instance, but it's not nearly as efficient as what we've managed to do with steam turbines and stuff like that. So steam turbines are what we use to make electricity from nuclear power, hydroelectric power, and coal-fired power plants. They basically just use that source, whether it be nuclear energy, coal burning, or hydroelectric. They use that stuff to actually heat up water. The water boils, becomes steam, then the steam runs through the turbine, spins the turbine. The turbine has little magnets on it that runs through a circular loop of wire, or many loops of wire, that creates electricity. And all that, of course, is done with a certain efficiency. And that efficiency for those best GE model turbines is on the order of 50-60%. So that's really amazing. Whereas a car might be 35%, your body might be 40-38% or something like that. Okay. So I guess that's the rest of the actual topics. I've given you a lot more of description of some of the how to solve some of the harder problems, and I've actually given you a lot more of the background information to sort of understand the concepts, and less. I didn't work quite as many examples because I think the examples that your book gives are plenty sufficient here. So I would make sure you know all those examples from chapter 8, that you can do them with the book closed. And then next time we'll learn about momentum. And momentum allows us to do something that conservation of energy can't. It allows us to deal with collisions, and allows us to deal even with collisions when energy is not conserved, specifically what we call inelastic collisions. So that's what we'll start on next time. And you folks are free to go. Don't forget to take your makeup midterm if you missed it. I don't want to have to drop people, but I'm going to have to if people miss this.
Thank you,
Other than that,
Professor.
you're free to go. Thanks for coming, everybody.
Thank you. Can you stay after class for a second so I can ask you a couple questions?
Yeah, no problem.
All right.
I actually have one question as well.
Go for it. You need something private, or?
No, it's not private.
Okay.
One of the assignments that you gave us was the answer the questions on page 75. I'm not sure exactly what that pertained to, but I did turn that in. I wanted to know, like, when was that due or something like that?
Usually when I do something like that, it should be due. I want it like usually within the next day or two, but I take it to the end of the semester. So if you've already turned it in, I'll be putting it in your gradebook. Did you send it to me by email, or did I actually make a link for you to turn it in?
I turned it in via Canvas. It's under. It said submit assignment, and that's how I.
Okay, that's cool.
Okay.
Yeah, I should find it. And that's going to be basically at the end of the semester when I take all your homework points. There's a certain number of points per homework assignment, and I add up all the ones that you're required to do, and I divide that number by the number of points you have. Now, if you have a bunch of these extra credit ones, then that number is going to be quite a bit bigger. And actually, I divide it the other way around. Sorry about that. And that actually gives you what your homework grade is. So that's how you're actually getting improved points. I've had people, for instance, get 108% on their homework. So instead of 20 points, they got like 22 points towards their total grade just from homework. So they can bring your grade up a significant amount. So that's how that'll work. Anybody else?
Professor, I was the one that sent you the email about the late homework that
Yes.
I just
Yeah, I
wanted to
saw
see
that.
if you like looked at it and saw what happened, I guess, in the system.
Yeah, the two times I remembered to look at your email, I wasn't anywhere near it. I'm going to look at it right after we finish ship here. So I'll send you an email probably within the next 30-45 minutes.
All right, thank you very much.
No problem.
Yeah,
Andy, yeah, go ahead, Lauren.
couple of the extra credit assignments in Canvas, they only go to like certain tests that pass, or can you still do them and they can go to like a couple tests that's coming up?
I assign them to whatever I told you when I originally did it. So I've got that like written in the assignment. So if I did that, it said I was going to apply this to test 1. It's only going to be the test 1. But in other cases where you just do an extra homework, so that's just going to apply to your net homework score. And if your homework's worth 20%, that means if you got a perfect 100, you get 20 points towards your total grade comes from homework. But if you got an extra credit, it might mean you get 24, and that's 4 extra points on your final grade is a huge deal. So that's how that works, Lauren.
Okay, and where can I see some of this extra credit at? That's in Canvas, or that's on
You'll see them
OpenStack?
actually in mastering. When you get to mastering, some chapters will be named chapter 9 extra credit or chapter something like that, extra credit. I don't know if I have any in there yet, but I will. And like I said, I have had some problems where I've asked people to do those. For instance, if you did that one today and try to find a better explanation of whether it has a maxima, that would be a great problem. But as you can tell, I had some problems with it, so it might not be one you want to try. But I'll certainly give you some points for trying that. You know, the one with the spring cocked and the shooting up the ball and trying to find the velocity as a function of height. If you can find a maximum on that in any way, I mean, whether it be brute force trying all the individual multiple decimal points, 0.03999999, you do something like that, I can give you significant points that way.
Okay.
And this is recorded, so that's good. Everybody will see it. How about Brett? You got a question, or Jessica Soto? All right. Lauren, do you have any more before you go?
Not at the moment.
All right. Well, y'all know my emails. I guess I'll see you guys later. And Miguel, you wait around and you should be able to have someone come soon. And Jessica, you didn't have any questions, right?
No,
I think she might be
did.
gone.
Turns out she does.
Oh, you do? Go ahead, Jessica.
So I actually sent you something in the chat.
She sent you something in the chat.
Okay, let me check that real quick. Oh, I see. Yeah, there's a message there. Okay, I tell you what. Yeah, I can put you in a breakout room. Okay, the breakout room's open. Jessica, if you want to go there, and Lauren, if you want to wait too, you can go there, and I'll talk to Miguel, and I'm going to go ahead and pause the recording right now.